Hello, I'm James Chambers. I am in AE 2610 in lab A02Y, and this is my third lab, digital sampling. So let's get into the motivation for this lab. In all engineering fields, time-variant signals must be measured and analyzed. In modern engineering, these signals have to be measured electronically at rates of many times per second. Frequency analysis and sampling theory are essential to good results when collecting these signals, so it makes sense for us to want to get a basic understanding of digital sampling and sampling theory. To get into the introduction and background, sound waves specifically are time-dependent waves comprised of the sum of many sine waves. Sums of sine waves can be analyzed as sound via the time history or undergo Fourier analysis to be analyzed as power spectra. Fourier analysis returns the pure sine waves that comprise a complex sound wave. Getting into the lab materials, this lab used the SimpleDAC software, which was the software we used to analyze and sample the audio data. It contains sections for both power spectra and time history. We also used the LabJack DAC device. This was the hardware that went along with the DAC software. It was a microcontroller with ports for audio jack connector and a microphone. The microphone was a simple microphone that's able to pick up sound signals from the environment. The audio jack allowed direct connection between the DAC and a computer, which could generate an audio tone. And finally, we use male-male wires to connect the microphone, audio jack, and lab DAC. The first of the week 2 experiments, we had to identify 11 waveforms. These waveforms included sines, triangle, square, ramp, and noisy sine waves, as well as the sum of sine waves, a product of sine waves, and a sine of sine waves. Um, these all had these had frequencies. Some of them had several frequencies or varying frequencies, and we analyzed the principal frequencies using the power spectra tool. In addition to waveform identification, we were asked to perform 6 more experiments as part of the week 2. First, we looked at complex waveforms. For complex waveforms, the power spectra is especially useful for analysis. It shows the amplitude of sine waves that, if added, would produce the complex wave. We analyzed square and triangle waves and found that square waves have more power at high frequencies than triangle waves, since triangle waves more closely approximate the sine waves. Then we looked at quantization error, which essentially boiled down to noise increasing as volume or amplitude decreased. Next, we looked at sampling rate. We discovered that the number of discrete points in the power spectra is equal to the number of samples divided by 2. The resolution is equal to the sampling rate divided by the record length. The range of the frequency of the power spectrum is from 0 to x, where x equals the resolution times the number of discrete points minus 1. Now on to the next 3 experiments. In part 3, we observed aliasing, where we found that to properly sample a wave, we must take samples at least twice the signal frequency. This is called the Nyquist frequency. Otherwise, our power spectra will be wrong, leading us to incorrect analyses. Then we looked at noise. We discovered that the type of noise in the tracks with noise present was white noise, which is random noise. For track 7, the signal to noise ratio was about 125, whereas for track 8, the ratio was about 28. Finally, we looked at a low-pass filter. For the low-pass filter, all sine waves that help make up a signal are muted if they fall above a cutoff frequency. To mute the 10 kHz component of track 9, the frequency of cutoff had to be about 9800 Hz. Following the week 2 testing, we were asked to test the microphones, where we played several signals with frequencies between 100 and 5000 Hz, and then measure the amplitude when connected directly via the audio jack or the microphone power, or uh, observe via the microphone, and then we measure the relative response of these two. Now for my personal experiment, I wanted to analyze the sounds made by different motors operating at different speeds. The acoustics of mechanical systems is a topic under active research, and understanding the basics can be essential to one's engineering skills. That was kind of my motivation. And I will consider this experiment a success if I can create a relationship between actuation speeds for different motors. Here we can see the raw data I collected, with each of the motor types being a small and large servo and a DC motor with and without a fan. We can see the power at a low speed, a medium speed, and a high speed. In general, this seems to increase as speed increases for each of these, but we will look at this more in the filtered data. So here is our reduced data. We can see that for most of the motors, the noise increases as the speed increases. However, for the small servo, this turned out not to be true. So after conducting my experiment, I thought of several ways I could mitigate the errors that I saw. I think I could define a microphone distance. As it was, I just tried to have the motor actuate as close to the microphone as possible, but I should have had a defined distance so the results could be consistent. Secondly, I should have based this on angular velocity of the motor since the servos and the DC motor are operating on different time scales or different scales of speed. Results may be inconsistent. Finally, I believe that this experiment was a success and that I was able to show that increasing speed and loading does increase the amplitude of audio response. However, it is clear that there are errors here and that there could be additional things done to improve this experiment. And finally, here are my notebook pages. We see the first two and then the table of contents. Thank you.